Okay, and welcome back to Fully Theoretical. We are back with Khan Academy, looking at polynomial division. And here things just ratcheted up just a little bit by including higher degree terms and full expressions versus the previous ones just had x as the denominator. So we're just going to work through this one together. Oh wait, hold on. I have my headset on. Let me turn that off real quick so we can actually hear what's going on. So there we go, that's off, and here we go.
This polynomial division business is a little bit more fun than we expected, so let's keep going. So let's say that, like I said again, someone walks up to you in the street and says, what is x squared plus 1 divided by x plus 2? So pause this video and have a go at that. And
Okay, so x squared plus 1 over x plus 2. And I haven't cleared that off. So we need a new layer. So x, let's switch to black actually. So x squared, was it plus 1? So we have x squared plus 1 over x squared plus 2. Okay. So the previous method of just using 1 over x in this case would essentially be 1 over, that is not a 1, 1 over x squared plus 2 times all of that. And you know, maybe we could get through it, but it's kind of a unelegant way of doing it. And when we have larger and larger expressions, you know, that's not going to work out very well. So we're going to not do it that way. And also, this is wrong. It's not x squared. It's x plus. Did I say why can't I remember this stuff? So it's x plus 2. So I didn't even get the 1 right. Okay. So there's actually a trick to this. So you'll notice that this is a second degree polynomial, but there is no first degree polynomial. And this is a first degree polynomial. And maybe we can do it without on this one, but the proper way of doing this is not like this. And I'll show you why. So basically, if we just work it like this, so x plus 2 goes into x squared plus 1, x times. So that's how you get the x squared to be down here, is to have an x up here. And then plus 2 times x plus 2x. But you'll notice there's a thing missing here. And the other thing on this, again, this is a smaller one, so maybe we could get by without, is you want this to be sitting above the same degree. So right now this is sitting above the second degree term. So the way to set this up is actually like this, plus 0x, because even though there aren't any first degree terms, when we're working through this, you're going to create a first degree term when you divide it. So plus 0x plus 1. So x goes into that, x times x squared plus 2x. And so now it'll make sense. So we subtract that. So that becomes 0. This becomes negative 2x. And now we can drop the 1 here. And x squared plus 2 goes into negative 2x plus 1, negative 2 times. Negative 2x minus 4, like that. And so that's 0. This is 1 minus 4 is negative 3, and that's the remainder. So it's this with a remainder of negative 3, where x does not equal negative 2, because if it's negative 2, then it's negative 2 plus 2 is 0, which means this wouldn't be true anymore. So that is, I guess this whole thing here is the answer that he's looking for. So let's pull back open the video.
I'll give you a little bit of a warning. This one's a little bit more involved than you might expect. All right, so there's two ways to approach this. Either we can try to re-express the numerator where it involves an x plus 2 somehow, or we can try to do algebraic long division. So let me do the first way. So x squared plus 1, it's not obvious that you can factor it out, but can you write something that has x plus 2 as a factor, and interestingly enough has no first degree terms, because we don't want some weird first degree terms sitting up there. And the best thing that I can think of is constructing a difference of squares using x plus 2. So we know that x plus 2 times x minus 2 is equal to x squared minus 4. So what if we were to write x squared minus 4 up here, and then we would just have to add 5 to get to plus 1. So what if we were to write x squared minus 4, and then we write plus 5? This expression and that expression up there, those are completely equivalent. But why did I do that? Well, now I can write x squared minus 4 as x plus 2 times x minus 2. And so then I can rewrite this entire expression as x plus 2 times x minus 2, all of that over x plus 2, plus 5 over x plus 2. And now as long as x does not equal negative 2, then we can divide the numerator and the denominator by x plus.
Okay, I mean, yeah, he makes a point, but this only works if, well, I guess completing the square, I guess the whole point of completing the square is because you can format it to fit the denominator. I just feel like this is a more complicated way of going about it, but okay.
Plus 2. And then we would be left with x minus 2 plus 5 over x plus 2, and I'll put that little constraint if I want to say that this expression is the same as that first expression, for x not equaling negative 2. And so here, we say, hey, x squared plus 1 divided by x plus 2 is x minus 2, and then we have a remainder of 5. Now let's do the same question, or try to rewrite this using algebraic long division. We'll see that this is actually a little bit more straightforward. So we are going to divide x plus 2 into x squared plus 1. Now when I write things out, I like to be very careful with my...
And apparently that was the point. I missed that.
I guess you could say my different places for the different degrees. So x squared plus 1 has no first degree term. So I'm going to write the 1 out here. So second degree, no first degree term. And then we have a 1, which is you could use our 0 degree term or our constant term. And so if we do the same drill, how many times does x go into x squared? We'll just look at the highest degree terms here. X goes into x squared x times. That's first degree, so I put in the first degree column. X times 2 is 2x. X times x is x squared. And now we want to subtract. And so what is this going to be equal to? We know the x squareds cancel out. And then I'm going to be subtracting negative 2x from, you could do this as plus 0x up here, plus 1. And so you're left with negative 2x. And then we bring down that 1 plus 1. X goes into negative 2x, negative 2 times. Put that in the constant column. Negative 2 times 2 is negative 4. And then negative 2 times x is negative 2x. Now we have to be very careful here because we want to subtract the negative 2x minus 4 from the negative 2x plus 1. We could view it as this, or we could just distribute the negative sign. And then this will be positive 2x plus 4. And then the 2x and the negative 2x cancels out. 1 plus 4 is 5. And there's no obvious way of dividing x plus 2 into 5, so we would call that the remainder, exactly what we had.
Wow. So let's see what I did. Plus and plus. Go back over to the video. Plus and plus. So we see that the problem was initially set up properly. So 2x plus, x squared plus 1 over x plus 2. X squared plus 1 over x plus 2. Okay, that's right. X plus 2 goes into x squared x times, so that's right. So we subtracted and we got the negative 2x. So then x plus 2 then goes into, should be marking this up. So that one's correct, like that. X goes into, well, first of all, X goes into here, negative 2x, negative 2 times, so that's correct. So negative 2 times x plus squared, x plus 2, man, you can tell I'm struggling here. So negative 2 times x plus 2 is negative 2x minus 4. So that's correct. This is also correct because we dropped the 1. Okay, so that's correct. So far, everything's looking correct. So we have negative 2x minus 2x is 0 because it's minus. And here's where I made the mistake. So that negative becomes a positive when you subtract it, because subtracting is the same as adding. So that's embarrassing. So the remainder should actually be 5 because we're essentially adding. And there we go, that should be 5. Did not get that correct, but I mean, that's the whole point of doing practice problems, is that you work out your mistakes in a way where they immediately give you the answer, and it's not a big deal. So anyways, thanks again for watching. I might do another one here where we work on some of the practice problems. Thanks, bye.